I'm guessing this is as many folks as we're going to have, so I'll start the show and the recording. Hi, folks. Not rhetorical. Hi. And hi, Zoomers. I have the class website up here so I can make sure we're all on the same page with respect to the work that is forthcoming. So I had a chance to go through homework 3 and update grades this morning. Let me know if you have any questions about any of those things that you may have missed. The next thing that you have due is on next Monday, you have a plan for your homework 5. So your goal basically is to figure out what data set you're going to use and what variables to use in that data set. That's your plan. So I am asking you to submit your plan so that I can weigh in on your plan. I said, I think 4 to 6 variables, preferably using something you've learned in here this semester. If you've had other coursework that you want to incorporate, like if you wanted to do a multi-level model that's generalized and you know how to do multi-level models, I'm okay with that. The idea is for this to be something that would be useful to you in the context of your research or your employment. So double dipping is encouraged, folks, okay? If you're already working on a project, turn it in for this class. That's the goal here. So 2 points for submitting a plan through ICON. I will give you feedback and send it back to you. And then your actual completed analysis is not due until the 24th of April. So we still have 3 or 4 weeks for that. The instructions for it are here, but note this is not a project. The idea is that this would be the same scope as a typical homework assignment. I'm thinking maybe 4 to 5 pages of text altogether. I just need a couple paragraphs for an introduction so I know what your questions are, enough about the method so that I can follow the sampling design and the variables, a results section of what happened in like a 1-paragraph discussion. That's it. So it's not a project, not a term paper, just something that would be like the core ingredients of a paper that you could then develop into a full manuscript, submit as a conference proposal, something like that. So if you have questions about what would work for this, or if you don't have data available, inside the plan document linked here, I put a couple websites where there are public use data readily available that you can download and use. If you don't want to use those and you're still looking for something, talk to me. I may have examples that you can use, but preferably it should be something from your world that you already care about. So if you've worked on a project in the past or you have people in your lab working on something, those would be the places that I would recommend going to. Other thing that you can be working on is homework 4. I released early, so it's not due until April 10th, about 2 weeks. But this is going to be a more complex model. So I'm just giving you the heads up that it's back to interactions again. You know it. And so this one will be more complex than the last homework. So I would start on the early side if you are able to do so. It's on count models. Only, not 2 models, but 2 different distributions. So 4 models in total. Then we'll have 1 more formative assessment. And then your last homework will be due at the end of finals week. It's not any bigger than all the rest of them. It's going to be on a path model, actually. So most of it will be the work of just estimating the model and finding all the estimates using a different type of software, M+ in particular, or Levon in R. So any questions on any of that? Zoomers, any questions from y'all? Nope? All right, fair enough. Then we still have a little bit left in terms of looking at predicting a proportion correct outcome. And then I also had put links up to another handout, basically other kinds of skewed continuous outcomes. And so I have some models to go through, for example, 4B. We'll see if we get there today. I don't think we will, but I thought it was possible, so I moved it into this spot. All right, so where we were last time is predicting proportions correct as an example. So why can't I just throw this into a regular linear regression model and call it good if I have a proportion as an outcome?
Because the residuals aren't independent, right? You can, like, they're directly related. There is enough residuals. Something about it is directly related to the mean.
The variance. Yeah, so the residuals are still supposed to be independent across persons, but the variance is tied to where the mean is. Yeah, so you'll have the most variance around proportions in the middle, and then the variance necessarily has to shrink the closer you get to the boundaries, right? So proportions have two boundaries, don't they? What's the worst you can do? 0. What's the best you can do? 1 or 100, depending on if you're thinking of it as percent or proportion. So what kind of link function should we be considering then for a two-boundary outcome like this? Logits, yeah, the logit family, I would say. Logit, probit, log-log, cumulative log, complementary log-log, excuse me. Any of those that are meant to keep things within the two boundaries. But in this case, the big task that we have is what kind of distribution goes with this. So the Bernoulli distribution is for 2, a binary outcome. We're switching to binomial, which Bernoulli is a special case of. Binomial would be for like basically multiple dichotomous outcomes that have been either summed or averaged into the number correct or proportion correct. Binomial is a distribution that only has one parameter, p, for the mean. You multiply that times the number of trials and you get your predicted number correct. So the parameter we're estimating is the probability of getting any one trial correct, essentially, any one item correct. And that translates into proportion correct when all is said and done in the model. So we looked at a couple models last time. Might be good to go back through them. So I'm using in Stata GLM, and in R I'm using VGLM. And I'm starting with an empty model so that I can figure out what my outcome is. So that way I can have confidence in my software, and also potentially if I were going to do any kind of likelihood ratio test, this would be a baseline model against which to compare more complex models. So I end up with, in my empty model, predicting an outcome for number correct, taking into account the number of trials. I end up with this number right here, 2.45. That is in logits. So to figure out what that means in probability, that's my inverse link. E to the logit over 1 plus e to the logit gives me 0.92. So 0.92 is the mean of this variable. It is the average proportion correct. Excuse me. In terms of the distribution fit, we're in bad shape so far. So Pearson chi-square over degrees of freedom is an index that we can use to determine if the amount of variability in our residuals is consistent with what the model says it should be. So if it is consistent, if this is a good distribution fit, this number should be close to 1. And the fact that it's 21 means there's 21 times as much variance in my residuals as what the model thinks. That's not good. Coughing to death is also not good, as it turns out. And I'm not even sick anymore. All right. So then we looked at adding 2 predictors. So this is remember what the outcome story was for this? This is predicting performance on a measure of grammatical understanding in young children who either were diagnosed with specific language impairment or do not have that condition. So we are asking whether this performance on this test differs between those 2 subgroups. We're also controlling for mother's education in years as a covariate, because in this field, that's one of the covariates you always have to have in your model or someone will yell at you. So just 2 predictors in the story because the rest of the story is sufficiently complicated. So I threw those in the model as well. And we looked at output for this, right? Does that sound right? I think we did, if memory serves. So I'll go down to the R section here since we did the Stata before. So link equals logit link within here. Within the formula in parentheses is number correct and number incorrect, whereas Stata takes number correct and number of trials in its formulation. And this number right here, who's feeling brave? If you were to put it in a sentence. The number is 3.07 and it's labeled as intercept. .07 tells me what? Mm-hmm. Exactly right. This is the logit of the probability of getting any item correct for the reference groups, so not having language impairment and a mother who has 12 years of education. And 3 is a very big logit. And in fact, if you work that out to what it would be in probability, it's 0.956. So that is the expected proportion correct for a child without language impairment with a mother who has a high school degree. And then we looked at the effect of NLI versus SLI. How would I talk about that slope? Minus 1.22. The variable is coded such that not impaired is 0 and specific language impairment is 1. Zoomers, you can play along too. You can talk or type, your choice. Negative 1.22. It's a slope. You know what slopes do, right? Change in y for a 1 unit change in x. So if we put the slope into the story, change in y becomes, what is y in these models? Yep, the logit of the probability of getting any item right. What happens to that logit?
So if you have SLI, it decreases by 1.2.
The logit. Yes. Yes, exactly. So the logit of the probability decreases by 1.22 if you have SLI. So that means you are less likely to get any item correct if you are in the SLI group. And I attempted to do the math last time, and that did not go well. To put it back together again, what the prediction would be. Yes?
I guess I'm just kind of confused as to like why it's SLI instead of NLI for that slope.
Because in the coding scheme, NLI is 0,
Okay.
and SLI is 1. So the slope always applies to the 1 group.
Right.
Yep. So if I wanted to come up with the predicted probability of getting any answer correct in the alternative group, then I have to start by generating a predicted logit by putting those two numbers together. So 3.07 minus 1.22 gives me the predicted logit in the 1 SLI group. Then I would convert that predicted logit into a probability. The only thing that I could do to this slope is turn it into what as an effect size? Odds ratios, yeah. That's going to be the answer like all the time in this class. E to the slope always turns out to be the effect size. The only question is what we call it. It's an odds ratio if you're doing binary, ordinal, or any kind of logit outcome. It's an incident rate ratio if you're predicting a count, but it's still E to the slope. It's called something else in Stata for nominal outcomes, and I don't remember what the acronym was, but it is still just E to the slope. So E to the slope is pretty much, you can't go wrong on that. What would the odds ratio be for this slope? And I'm going to give you 3 choices. Less than 1, 1, or greater than 1. My slope is negative. What kind of odds ratio am I going to get back? Yeah, it's going to be less than 1. Above 0, but less than 1. So that's what gets tricky, I think, about interpreting these things is that if you're in logits, I can look at the sign of this and go, yeah, the one group goes down because this is a negative slope. But that is always going to turn into a positive number when expressed as an odds ratio. So you can't look at the sign anymore. You have to look at the number. If it's less than 1, then it corresponds to a negative slope. What about kids whose moms have a lot of education? What happens to their predicted probability of getting any answer right? Yeah, goes up significantly at this point, by the way. After we incorporated these two predictors, our Pearson chi-square index of fit is still 15. So it's better than 21, but still nowhere where it needs to be. So what this is telling me is that the model does not have enough variance in it for this outcome. The variance that is dictated by the binomial distribution by itself is insufficient. The residuals have 15 times as much variability as what the model predicts. So if the model doesn't have enough variance, then that means these standard errors are too small or too big. If the model doesn't have enough variance in it relative to what it should have. Too small, yeah, because standard errors come from your variance model. And if my standard error is smaller than it should be, what does that say about my p-value? Smaller than it should be. So we should not yet trust the inferences we're making when the model does not adequately capture all the variability in the outcome. Here are the odds ratios, by the way. That slope of minus 1.22 corresponds to an odds ratio of 0.29. So I built that myself in R by accessing the coefficients that were stored in the model and then asking it to spit out a confidence interval for those coefficients, same as usual. All right, questions so far? So here are some choices for how we can try to fix it. The model for the means, the fixed effects are going to stay the same throughout everything. We're just changing what we're doing with respect to the distribution. So do you remember how we fixed it when we had Poisson? Poisson model is the same, Poisson distribution is the same type of problem. It only has one parameter and it says the mean and the variance should be one number. If there's more variance than what the model predicts, how did we fix it back then? Yeah, negative binomial, which builds on Poisson by adding like a stretchy factor that allows the variance to exceed the mean in a quadratic fashion. That's going to be one option that we look at. But there's another one that shows up in these models for modeling overdispersion that's additive rather than multiplicative. So I want to show you how to do this because it seems like a trick. But this is the only version that I was able to find in the context of a multi-level model for proportion correct outcomes, additive overdispersion. The term for this, you will also see this in the literature as referred to as an observation level random effect. What we are doing is adding to the model another source of variability that is one term per person, and we're estimating the variance of these terms across people as the model parameter. So we're essentially building back in something that looks a lot like a separately estimated residual variance back that we had in regular general linear models. It's the same type of concept. So that's supposed to soak up all the extra variance and then render what's left purely binomial. That's the way it's supposed to work anyway. So technically speaking, this is a multi-level model at this point, even though we only have one dimension of sampling. It's a trick. So that means that we have to switch what particular functions we're using. In Stata, there are a whole bunch of functions that start with the letters ME. Me. That stands for mixed effects. So if you have longitudinal or multi-level data, then you look for the corresponding function based on what type of outcome you have that starts with ME. So MEGLM means mixed effects generalized linear model. It's situated similarly in that we have the outcome, we have the binomial with number of trials telling it link equals logit, and we have this thing. This is the different part right here. What that is doing is saying, hey, can I have a separate residual for each person? And people are organized by this variable ID. I had to change the method of estimation to be able to do this. This is a type of numeric integration that is essentially thinking that you only have one integration point. For those of you familiar with these models, you can ignore everything I just said. It's still maximum likelihood, but harder to do functionally. So in this model, we have this extra parameter that shows up in the output. That is essentially my residual variance. It's the variance of this new random intercept thing. So it's extra variability that's being estimated that adds to the variability predicted by the binomial model. So it doesn't scale as a function of the mean, it just adds. Stata helpfully gives you a likelihood ratio test against the model that does not have this extra source of variability. So the height of the data improved by 981, which means, yeah, definitely that would be something we would keep. Nothing in here directly tells you about distribution fit, but I was able to get that out of R by doing it manually. Here are the odds ratios for these. In R, I am using a function called GLMER, glimmer, as some people say, generalized linear mixed effects regression. And this part right here on the end is how I add the extra variance term. It's called a random intercept. It comes up with the same estimate for the variability across people of this extra term. And now the Pearson residual for my distribution fit is actually less than 1. So now it looks like there's too little variance in the model because all of it went to this separate residual term that we added. In terms of the conclusions that we would draw, the standard errors are much bigger because now they're incorporating more variance than what the model had before. The effect of NLI versus SLI is still significant, but the effect of mother's education is now non-significant. So quite a different result relative to the previous model. So far this one looks relatively best, although the fact that the variance does not change as a function of the predicted mean means it's probably not ideal, but again, this is the only way that I know how to do these models if you have a multi-level or longitudinal type of design. In R, I had to do my own likelihood ratio test because the packages that they have to do this don't necessarily work across all the different types of models, so I did it manually. I think I've shown this to you before, but it's been a while, so we can go over it for those of you who are using R. What I'm doing is asking it to access pieces of saved output. So inside the model that I labeled bin for binary, or binomial, excuse me, and this model currently I labeled model bin add for additive overdispersion. The log-like is referring to the log likelihood of the model as a saved number. So I don't have to actually type the number in. It will just go into the stored results and find it. So I'm taking the log likelihood from the model that has fewer parameters minus the log likelihood from the model that has more parameters, and then multiplying that result by -2. So that's the difference in -2 log likelihood. That is being saved as an object called deviance test A. That's what dev test means. I'm then using a function for getting a p-value from the chi-square distribution, which I called regular p-value, degrees of freedom 1. I can cut it in half to create what is known as a mixture p-value. So mixture p-values are necessary when you do likelihood ratio tests for any new term in which 0 is the lowest it could be and is also the null hypothesis. So this extra variance term that we added can't be negative. So the 0 is for the situations in which it wanted to go negative, but it couldn't. So you can cut your p-value in half, but with a likelihood ratio test statistic of 981, it doesn't matter. So either way, it's wildly significant. E to the minus 215, 215 zeros before the first digit or so. So this is definitely an improvement, but it's not the only option in town. The other one I wanted to show you is what's known as a beta binomial. This is analogous to what happens with the negative binomial. It's taking the binomial and adding a scaling factor that stretches the variance. It allows more variability as a function, a multiplicative function. Different textbooks and articles that I've read have phrased this differently, and so this is my best guess as to what the model implied variance is at this point. This is the new part right here that takes the variance and extends it, essentially. So we get this parameter shown up in our output, either that version or inverse of it or the log of it or something. It varies across packages, but that's the new thing that we're estimating to make extra variance happen in the model. In Stata, they don't have this built in. Somebody had to write a package to make it. So you can download that package. It's called BetaBin that fits this model. The syntax for it is very much the same as the other ones, though. We define the outcome as number correct. We have the number of possible trials within this piece of the code. We have the link equals logit, and there's no options for distribution because there's only one built into this, the beta binomial. So then we get the new scaling factor in two different metrics. One is 1 over the scaling factor that was in the equation here, that thing, 1 over that. And they also give the log of it, for whatever reason. So basically what this boils down to is testing whether the new terms are different than 0, whether we need the extra variance in the model, which we will need to do a likelihood ratio test for that. They thoughtfully did this for us in Stata. So there's the test statistic for how much taller the model got relative to straight up binomial. Again, huge result, so yes, this is still better. And if we look at the conclusions from it, same pattern. The effect of SLI is still significant, but the effect of mother's education is no longer significant in this model relative to the initial binomial. In R, here's the effect sizes. E form is what you type to get odds ratios, which they just call it e to the beta as the label for this. In R, I'm still using VGLM, but now the family has changed into this thing. And I honestly have no idea what L row is. I just found an example of it, and I fought with it until I could get it to work. So it seems like this is redundant because it's referring to two different logits, but it's still just one model in terms of what we have predicting each outcome. It's one submodel. The rest of the code is structured the same way in terms of how you tell it number correct versus number incorrect. I could not get distribution fit out of Stata because it didn't do it for me, but in R I can do it, and it's 1.8. So at this point, this is the best result that we have. It's not too small, it's not 21. So this tells us that we're much closer to the amount of variance that's actually in the data at this point. Not perfect, but much closer. So these results would be more believable relative to the ones for the binomial. So here's another likelihood ratio test done manually where I'm comparing the beta binomial against the regular binomial. The difference is wildly significant as before. I'm also going to compute another type of effect size in terms of an R-square. So because we're back in the situation where the outcome is on the same scale as the predicted outcome, we can do a total R-square. So what this piece of code is doing is saving a new variable to my data set that I have named pred beta bin for predicted from the beta bin model. It is taking the predict function, which creates predicted outcomes from the model fixed effects, in the inverse link metric. So this is going to give me predicted proportions for everyone in the data set. I can then correlate them. Here's core test to do that with the real proportions, save that result and square it, and that gives me something that I can interpret as an R-square. So back in linear regression, you could compute model R-square in two different ways. You could talk about it as how much of the sums of squares were reduced. We don't have sums of squares here, so I can't do that, but the other way you can do it still holds. R-square is the square of the correlation between the outcome predicted by the model and the real one. So it looks like SLI and Mother's Education as a set have predicted about 16% of the variance in this proportion correct outcome. Not bad for real data. That same process of generating a predicted outcome column and correlating it with the real outcome and saving the result can be done in Stata. I have that code on the previous section. Predict creates a column that's named this. Core asks for a Pearson correlation, and then I accessed the stored result and asked it to square it, and it printed the same number. So converging evidence across these. So on the whole, in this situation, you could use an R-square like this to convey effect size. You can also report individual odds ratio type things for your slopes to give specific effect sizes to each slope as well. All right. Two more, I think. How are we doing? So once you get the hang of it, it's like plug and chug. It's like, okay, what kind of link function do I need? What kind of distribution do I need? Within a family, you can use AIC, BIC, and often likelihood ratio tests to decide on distributions that are relative to each other. So like beta binomial adds on something to binomial, so those two are nested relative to each other. So within a family, you can use all of these things. What's difficult is to compare across families. There's no direct, easy way to be like, is normal okay, or do I need this beta binomial? Because those are from different distributional families. So the log likelihoods, the AICs, and the BICs would not be on a comparable scale because the formulas they use for height are not on the same scale as each other. Like normal versus beta binomial would be like talking about one in inches and something else in centimeters. Like they're not on the same metric. But within these families, you can compare across. So let me explain what I'm doing next with the picture. Here's my distribution, okay? This is what I'm modeling. I can't just look at this picture and automatically know what kind of distribution this corresponds to, because distributional assumptions are always about the leftover part, the residuals, not the marginal outcome. But a picture like this is definitely going to point me in a direction. I know that because proportion correct has two boundaries, I'm probably going to need some kind of logit type thing to deal with that. The fact that I have like these people down here pulling the distribution means binomial is probably not going to be adequate. But there's one more thing that I might want to be concerned about that this picture is going to hint at. It's the same type of concern that we had in dealing with counts. Too many ones, exactly. One inflation is what I would call this instead of zero inflation. It's the same deal. The question is, are there more people stacked in this column who got 100% than what my any distribution is anticipating? The binomial thinks there should be some here. Beta binomial thinks there should be some here, but the question is, do I have too many? Now, do you remember the choices that we had for dealing with this in count land? What were my two types of choices? Louder? Well, the process is analogous, even though Poisson is for counts and binomial is for number correct types of things. But how did we deal with extra zeros in count land, is my question. There were two different strategies we talked about. And I showed you one of them. I didn't get a chance to show you the other yet. Yeah, one is to separate them. So both of these strategies to deal with, in Countland, it was extra zeros, but it's going to be the same here with the extra ones. One was to split them. So then you're building basically two submodels where one submodel is, are you a 1 or something else? And then if you're something else, what are you? So it's like dividing up the sample. That is what's known as a hurdle model, or a two-part model more generally. The other was to try to predict the logit of being an extra 0, and that's what's known as a zero inflated model. So that one is not splitting up the sample. It's simply trying to address the fact that there's this pile up on one end and allow that to happen. So I went looking for how to do binomials with one inflation, and the internet let me down. I know, Google University did not teach me how to do this. Shocking. So I was like, you know what? I can fix this. I'm going to take this histogram and flip it around. And we're going to predict number incorrect. Because if I predict number incorrect, then what do I have? Zero inflation. Boom. So a little bit of creativity and a hack, and we'll get the job done. I don't need one inflation. I can make this work. So now, so that I can examine whether I have extra people here relative to what I'm anticipating, I'm going to do it with zero inflated models, first for binomial, and then for beta binomial. So the switch then, because I couldn't find one inflation, is to predict number incorrect. And do you think that my results will be any different if I predict number incorrect rather than number correct?
What do you mean by any different?
Let me be more specific, because that was not a good question. Here are the results from, let's go with the last model here. By the way, this is a homework 3 review as well. So this is my solution from the beta binomial predicting number correct, or proportion correct, right? That's what I have in front of me. So the intercept for the model, for instance, the logit of the probability of getting any item right for my reference NLI group, mom with 12 years of education, is 2.95. What's the logit of getting any item wrong? Times -1. Logits are symmetric. So if I predict number incorrect, this becomes -2.9. This becomes -0.04, and this becomes +0.97. Will my R-square change for variance explained if I predict number incorrect instead of number correct? Nope. Will the effect sizes change? In strength, no, but in direction, yeah. Yeah. So the effect sizes would look quite different because of the contraction between 0 and 1 of all negative slopes, whereas positive slopes get to have the whole rest of the number line. So it will create an apparently different effect size, but it's not actually different. So this is one of the beautiful things about logits, is the symmetry. So on your homework 3, there were a couple of questions that said something like, what's the logit of answering higher than this? And then the next question was, what's the logit of answering lower than this? And I was hoping to reinforce, logits are symmetric, it's times -1. The additive inverse, my math friends tell me. All right, yes, thank you, Zoomers. I'm watching the chat. So far, you're doing awesome at this as well. So in the same way that for count outcomes, you could add a stretchy factor, so go from Poisson to negative binomial, or you could add zero inflation, or both. The same is true in this. I could have straight binomial, beta binomial, binomial with zero inflation, or beta binomial with zero inflation. Having both may not be necessary. Either the stretchy extra variance or the problem of zero inflations could try to solve each other. So it's an empirical question whether you need both of those additions. That's why I'm going back to regular flavor binomial to see what that looks like. So in this model, I'm still predicting the probability of any trial being incorrect through a logit. So my predictor model is the same. But what I have added is a second submodel, what I call the zero model, for whether the probability of being an extra zero. This needs to be the word extra in there. Not just zero, but extra zero, beyond what is expected. So the logic, by having this be empty, only have an intercept, is I'm asking, what is the probability of being an extra zero? Because if it's really, really small, then it means I don't have any extra zeros. So it makes sense to ask whether I need it before trying to predict what they would be. So in Stata, I had to find another user-defined package called ZIB for zero inflated binomial. I found it in R, I think. Yep, BGLM had it. So this one has both. It does not tell me what the distribution fit is in Stata, but I was able to get it in R. So in terms of my solution, note that the p-values are all back to wildly significant again. So binomial doesn't have much variance, and adding the extra zeros doesn't appear to change that. The direction of the coefficients is backwards relative to what it was before for the same reasons. And then I have this extra piece right here, which is my inflation model. So this is the logit of the probability of being an extra zero, which is 0.41. So that's actually really high. According to this model, I have a big problem with having extra zeros. I had to do the likelihood ratio test myself in Stata because it wouldn't let me do it across different packages. So I found Stata code to be able to do those. I had to input the values because I couldn't figure out how to make it store across multiple runs, but this chi2 thing does the same thing in terms of generating a p-value. So the difference in -2 log likelihood relative to straight up binomial by adding the extra zero inflation is a difference of 543, so yeah, wildly significant. That would be a huge chi-square result. I have the odds ratios here for E form. That is the effect sizes that go along with those things. In R, I have, let's see here. These are the extra things that I had to find. Yes, question?
After you did the E form, the inflate constant thing is negative. Does that, like, I was just curious about that. Like, what is that?
This
Normally
didn't.
you wouldn't have a negative number with, like, an E form. Right?
Correct, you are right. This did not change.
Okay, so that just stays the same throughout, because it's just the probability of an extra zero.
It's the logit of the probability of an extra zero, and they could have turned that into an odds, but for whatever reason, the person decided not to. So it's the exact same number as it was in the original solution. Good catch. I believe I labeled that. Yeah, so if my label's out here, these are all e to the parameter. This one is not. An arbitrary distinction, but one that's potentially confusing. Speaking of potentially confusing, no potential, it is confusing. This is what I had to enter to figure out how to get my extra zero submodel included. It looks like if I were to try and read this, ion emp string 0 equals null, followed by 0 equals 1 mp straw 0. Any guesses as to what the hell that refers to? I have no idea, and the documentation didn't tell me, but I made it work. So if anyone out there on the internet knows what the hell this means, please tell me, because I would like to know. I find it dissatisfying when I can make something work but not understand it. But these are the options that resulted in a zero inflated binomial model. So it gives intercept 1 and intercept 2. Intercept 1 is the logit of getting any one trial incorrect for my reference groups. Intercept 2 is the logit of not being an extra zero. How do I know that? Because it's the same number that Stata gave me, but it's backwards in sign. So the submodel in R is predicting the logit of not being an extra zero, whereas Stata is predicting the logit of being an extra zero. Possibly that is something that I could fix with more options if I could ever figure it out. But that'll have to be for another day. But the reason I didn't try that hard, my Pearson chi-square is 13. So there's 13 times as much variance in my data as what this model says. So this is not a good model, even if it fits better. So what it looks like thus far, binomial doesn't have enough variance. Beta binomial looked much better. Now I'm testing for whether or not I need to add both beta binomial and zero inflation, which I was able to find in Stata. There's the extra zero. So I labeled it correctly this time. And the routine I found was ZIBBIN, zero inflated beta binomial. This one, the syntax is a little more understandable. The second submodel for zero inflation is specified by this inflate command here. And when I only have a constant in it, that means I want an empty model just to see if I even need zero inflation. So this is stretchy binomial, essentially. It has the extra variance built into it and a zero inflation submodel. So this is the analog to zero inflated negative binomial in Countland. So it is going to give me, these two refer to the variance multiplier thingy that differentiates it from binomial. This is my new zero inflation parameter. So this is the logit of the probability of being an extra zero, which is 0.25. So 25% of my sample would be extra zeros relative to what the beta binomial expects. Quite a lot. Looks like I need it. If I test this model against the zero inflated binomial, it fits much better. So it looks like in this data set I need both. And adding the submodel improved my R-square a little bit. It was about, I think it was 12% before. Does that sound right? Maybe I'm making it up. Here it is, 0.157 from before. And now it is, nope, a little lower. Makes sense, actually, in hindsight. It should go down a little bit because I'm letting those cases be extra zeros, but not saying why. And then just to round things out, I added beta binomial with zero inflation with predictors. So the very last model, this is page 12, is an example of how you could predict who is the extra zero. So I put in the same two variables that were in my regular model, so now my submodels are parallel in structure. It looks like neither variable is related to being an extra zero, however, whereas only, yeah, so now mother's education is significant, but the group is not significant, which is interesting. So it looks like it's sort of trying to recreate, both of these are working against each other in the separate submodels. So here is a comparison of all the information that I would use to decide what to keep in practice. So I built this table out of all of the results that we have. So if I start with just regular binomial, that distribution didn't fit very well. Adding additive overdispersion basically soaked up all the variance, so now we have too little variance relative to what we're supposed to have. Multiplicative scaling to make the variance grow as a function of the mean is decent distribution fit. Zero inflated binomial without that scaling is bad again. I had to re-estimate the zero inflated beta binomial in SAS to be able to find a Pearson chi-square, and it came up with that number, which is a little bit on the low side. But so far, that one looks like it's the best. So here are some results then, and what I would talk about. So as before, I described the process of figuring out which distribution I needed to use first, and then only interpreted the coefficients from the one that I landed on. That way you don't have multiple sets of results confusing your reader. Extra space notwithstanding. All right. The end. And no, you don't have a homework on this. Unless you want one, in which case, pick proportion correct for your homework 5, and then you can get a chance to practice these. But when I saw how complicated this was going to be, I was like, no, I can barely understand this. I'm not going to make you guys do it. As a general rule, something that I only figured out 10 minutes ago is not a suitable exercise for students to do. Fair, right? Yeah, so, but I wanted you to have it for your future reference. All right, how are we doing? Hanging in there? There's a thumb. Let's see. Let's see if there's anything I can do that would be not painful for today to finish with. Yeah, that's kind of a new topic, actually. Yeah, so there's a few slides on extra zero values and proportions that describe the zero inflated model. The hurdle model is something that I could not find because do you remember what we had to do to fit a hurdle in countland? What the count part had to be in that case? If we take all the zeros out of a count distribution and we move them to a different submodel, then the count doesn't have a zero in it and that's bad, but there was a fix for it. Do you remember what that was called? Zero altered or zero truncated? As far as I know, there's not a zero truncated version of a binomial or a beta binomial. So the hurdle option would not be appropriate unless we could find a similarly truncated distribution to do. That's why I did the expected one. All right. So what we have to do next time, we're going to end a little early today rather than try to push through, is other kinds of not normal outcomes. Because the type of outcome that you have doesn't always necessarily lend itself to the nice, obvious choice as to what you should do with it. So let me show you very briefly the picture that we're going to use as the basis for the next example. This is predicting housing prices in a data set I borrowed from the Agresti textbook, I think it was. So this is the distribution of housing prices in the sample, ranging from houses that cost, this is in thousands of dollars, I think from about $20,000 all the way up to almost $600,000. So if I look at this distribution, how would you characterize it? Does it look normal? Yeah, this blue line should match if it were normal. Looks skewed, I would say. Is there a boundary that I have to worry about in predicting something like house prices? 0, right? You can't have a negative house price. Like, I'll pay you, take my house from me. It doesn't happen. So this is not a count. It's not a proportion. It's something that is truly continuous. Like you could sell a house for, $200,060.52. Like, it's not just integers. But then we might also be concerned about what one would call outliers. So there's 2 houses out here that cost way more than all the others, and a few right here. So if I were going to do some kind of outlier trimming, how many houses do you think I should kick out? What's an outlier and what's not? These 2? They're far away. How about that one? Is that an outlier? How about that one? Yeah. Reasonable people could disagree on where to cut things. But how about from the perspective of reality? This is not an aberrant thing. You can have a house that costs $600,000. Like, that's possible. So from the perspective of not wanting to limit the generalizability of my conclusions, I should keep it in there. So the question is, what do I do with something like this? And I want to show you 3 options next time. 2 that are using continuous distributions, and 1 that does something completely different, which is quantile regression. So that's what's on tap for Thursday. Sound fun, right? Quantile regression, I think, is super cool. I should have learned this way earlier than I did, so I want you guys to have what I never had. But the basis of quantile regression is the idea of predicting the median instead of the mean, so that the outliers don't have as much influence. In the same way that you would report the mean as a measure of central tendency because it's robust to outliers. It's the exact same principle. Super cool. All right, 3 o'clock. We're going to end a little bit early. Let me know if you have any questions about what you should be planning for homework 5. I have office hours tomorrow as well. You can be working on homework 4 in the meantime. Thanks for being here, folks. I shall see you Thursday. Enjoy the rest of your garbage day.